is the port B and port C lower, that means PC0 to PC3, are connected to 8 plus 4, PB0 to PB7, PC0 to PC3. So total 12 switches, they are connected to the port B and port C lower part. And we need to write a program so that the switch's status gets reflected in these LEDs. These LEDs are connected to port A, PA0 to PA7, and PC4 to PC7, port C upper. So port C lower switch status should be reflected at the port C upper LEDs, and port B switches should get reflected into the LEDs of port A. So in this site, 8255A is interfaced with the 8085, and here you may see that A15 line of the processor's 8085's address bus, A15 line is, after knotting, it is fed to the active low chip select of 8255A. That means whenever A15 line is 1 CS bar of 8255A being active low, being activated, or the 8255A is selected whenever A15 is 1. Good. Now processor's 8085's address buses, A0 and A1 line is connected to the A0 and A1 pin of 8255A. Memory read, that is the combination of IOM bar and read signal. This is fitted to the RD bar and MEMW to the WR bar. Reset out. So 8085s is having with an active low reset in pin, through which sending a low signal, 8085 can be resetted. And 8085 also has a reset out pin. So that reset out pin of 8085 can be fed to the reset pin of other devices associated with the 8085. So that when 8085 is resetted, all these other peripherals will be also resetted. So 8085's reset out is connected to the reset pin of 8255A. Okay, here in this addressing scheme, memory map prio concept is used and linear select decoding is used. So the physical memory present in the 8085 or connected with the 8085, that should be restricted to 0000F to 7FFFH, so that no actual physical memory locations address should have A15 equals to 1. Okay, so now A0 A1 pin of the processor's address bus is connected to the A0 A1 pin of the 8255A. That will be internally decoded to identify port A, port B, port C, and control register within the 8255A. Similarly, which way the memory chip decodes the address lines so as to identify each individual memory registers within it in the same way. So here, according to this arrangement, port A address is becoming, if we consider other lines are don't care, and considering don't care lines are being 0, considering that the port A address can be 8000H. Other lines, that means A2 to A14, they can be anything. That will be resulting into the multiple addresses if other devices are not connected. Okay, so A15 must be 1 for selecting 8255A, and now becoming based on A1 and A0, the address of port A is becoming this one, port B is this one, port C is this one, control register is this one, based on A0 and A1 bit combinations. Now, to send, so we need to write a control word to the control register of 8255A so as to configure port C, port B as input port, port C lower as input port, port B and port C lower as input port, port C upper as output port, as LEDs are connected with them, port A as output port. So what is our control word? LSB bit should be port C lower, okay, port C lower should be input port, yeah, so 1 should be there, 1, here 1 should be there, port B 1, input port. In which mode? No handshakings we are dealing with, because LEDs and switches are always ready to communicate with processors. So port B should be configured, ports B and port C lower will be configured in mode 0. So here there should be 0, 0, 1, 1. Now port C upper, LEDs we have connected, so output port, 0. Port A, LEDs we have connected, so 0, D4 bit should be 0. Port A should be also connected in mode 0, simple input output mode, which does not require handshaking. So both 0, 0. For IO mode command word, D7 bit is 1. So what is our control word? 1000, that means 8. 8 followed by 0011 means 3, 83. See, MVIA 83, we have loaded into the accumulator 83 and we have sent 83 into the control register STA 8003. Control register address was 8003. If A15 is 1, A14 to A2 is considering 0 or don't care or 0, and considering A0 and A1, that should be 1, 1. So address is 8003. So you have sent the control word. Now, okay, get the data, get the port B switch status. Port B address is 8001 port B address. So port B switch statuses are being readed. STA, okay, LDA 8001 port B switch statuses are being readed and stored in accumulator. Now the accumulator content needs to be sent to port A, having with address 8000. So port B switch status according data we have sent to the port A where LEDs are connected. Okay, now port C lower has been configured as the input port. So this switch status should get reflected into the LEDs that are connected to the port C upper part. Port C upper part, PC4 to PC7. But if we read port C, only PC0 to PC3, this 4-bit information we have of importance. And that should be shifted to the same bit pattern should be shifted to the port C upper part so as to glow the LEDs according to the switches connected to PC0 to PC3. So we should read port C3 data, LSB 4 bits we are interested in. So we should shift it into the MSB 4 bit part. How? By using rotate left operations, by using rotate left instructions. 4 times I will be rotating. So this PC0 to PC3 status, then it will be reflected into the PC4 to PC7. So that bit pattern is to be loaded into accumulator. Within the accumulator, I need to rotate them towards left. Rotate them towards left, and then send the data to the port C again. So read the port C. Port A is having with the address 8000. Port B is having with the address 8001. Port C is having with the address 8002. So rotate left through carry, rotate left through carry, rotate 4 times I need to rotate, so that the PC023 bit pattern should get loaded into PC4 to PC7. Get the data loaded in the accumulator and left shift the accumulator data towards left 4 bit. So 4 RLC. Send it to the port C upper part, halt. I think program is clear to you. Okay. Now, another program. Let the problem statement is for interfacing circuit, to design the interfacing circuitry using 8255A in mode 1. In mode 1. Mode 1 means handshake or interrupt driven mode. So, and here it is mentioning that port A, problem statement, it is telling port A as an needs to be described as an input port for a keyboard which containing 8 switches. Not any matrix pattern of switches, but 8 switches only. So port A needs to be connected with the 8 set of switches or keyboard consisting of 8 keys. Input device. So port A needs to be configured as input port with interrupt IO. Okay. So that's why I have to go for mode 1. So port A needs to be configured as input port in mode 1. And port B needs to be designed to be connected to a printer with status check IO. Okay. So to port B we are going to connect a printer which is using status check IO, not interrupt driven. Okay, good. So port B also needs to be configured. Printer is an output device. Processor is going to send data to printer. So printer is output device. So it is connected to port B. So port B needs to be configured as an output port and in mode 1. In mode 1, that is programmed IO or status check IO. Okay. Now, as the keyboard, the previous days you may think about the printers were having with the 8-bit data, say 25 pin ports in previous days, parallel data transfer. Today the printers are equipped with the serial data transfer capabilities. So USB port you can connect. But in the previous days, say you may find the very old printers, the printer cable length, printer cable, it was of 25 pin, very thick wire, thick cable, very. And the very early days, not very early days, but we have also worked with that 24-bit cable in my projects. Okay, but today's serial, all devices are, communications are in serial mode. In previous days, they were in parallel data transfer. So 8-bit data parallelly needs to be sent to the printer. And some other signals were for handshaking, power, ground and other handshakings. Some may be redundant. Okay. Okay. Now, here port A must be having with the interrupt capability. to which keyboard is connected, 8 keys. So internal interrupt enable flip-flop of 8255A for port A, that needs to be enabled also. Internal interrupt enable flip-flop of port A of 8255A, that needs to be enabled by setting appropriate bit of port C in BSR mode control world. And obviously in the IO mode control world, we need to set up port A in the input port in mode 1, port B as output port in mode 1. But port B is using handshake, port A is going to use interrupt driven capability. Okay, then processor needs to know the output buffer full signal of port B to get the status, whether the printer is ready to print next character, then processor will be sending the next character to the printer. For dealing with keyboard in interrupt driven mode, the keyboard is supposed to send a interrupt signal to the processor, or 8255A is supposed to send effectively this acting as a buffer. 8255A is going to send a signal to the RST 6.5 interrupt pin of 8085 when a key is being pressed. Okay. Now, to read that key, or like that. Okay, now, so to the port A keyboard, to port B parallel printer, both port A and port B using mode A, mode 1, that is handshake or interrupt driven mode. Each of port A and port B using 3 pins of port C for providing handshake signals. Port A is using upper 3 bits of the port C, PC3, PC4 and 5 for interfacing with the keyboard up to this portion, and port B in mode 1 but using status check. So INTR B is not useful. INTR B is not useful. So port B is using 2 pins of the port C. Okay. SCK bar and output buffer full. This we have covered the day before. I think it was very clear to you. So, port C. Okay, for 8255A, it is having with 2 interrupt enable flip flops, one for port A, one for port B. And for supporting interrupts for port A and port B, the corresponding interrupt enable flip flops needs to get enabled. This is within 8255A. For enabling the generation of interrupt signal from 8255A to be fed to 8085. And also, 8085 is having with an internal interrupt enable flip flop, so as to enable one interrupt enable flip flop 8085 have, so as to enable or disable accepting of those interrupts that are coming from input output devices or PPI chips like 8255A. You should not get confused. 8255A has 2 internal interrupt enable flip flops, and 8085 for generation of interrupts. And 8085 is having with one internal interrupt enable flip flop for accepting an interrupt signal which may come from either 8255A or from any input or output external devices directly, which are not maybe interfaced with through 8255A. in the day before, the data ready pin of the ADC, while directly interfacing with the 8085 without using 8255A, that pin was going to generate of ADC, data ready pin was going to generate the interrupt signal to be fed to the 8085. But here 8255A is acting as the buffer chip, avoiding the connection of separate latch or tri-state buffers with IO devices. Now, devices addresses, now it will be, what will be the devices address? So here the IO mapped IO concept has been used, and absolute decoding, no linear select decoding. Entire exact 8-bit address bus has been entirely decoded. And you see, for CS pin to get enabled, this active low pin to get enabled, a low signal should reach there, which happens only if A7 to A2 all are 1, then this AND gate output will be 1, after bubble it will be 0, and 8255A it will be activated. So now based on A0, A1 and A0, different port address are FC, FD, FE, FF. For port ABC and control register of it. Good. So, what is the control word? Say to port A, we have connected to the port B, which is using status check mode, that is mode 1. To port B, we have connected printer, output device. So port B needs to be configured as an output port. This second bit, second LSB bit, it is for port B. It should be output port, so 0. Okay, port C lower. Okay, port A and B each are using around 3 pins from port C, and port to the port C remaining 2 pins we have connected nothing. So port C lower can be don't care, any bit, 0 or 1, anything. So let us keep it 0. Now port B and port C lower in which mode? Obviously in mode 1. That is for programmed IO or status check IO or interrupt driven mode. You know, mode 0 for simple input output port, that is applicable for simple input output device that are always ready to communicate with the processors. Mode 1 for handshake and interrupt driven capability. Mode 2, which is applicable only for port A, that is for processor to bidirectional data transfer mode, applicable for processor to processor communication. So port B and port C lower both are in mode 1. So that's why the D2 bit is 1. Now port C upper. Okay, port C upper can be don't care, because port A and port B using 3 pins of port C, and remaining 2 pins of port C we have not connected anything also. So don't care, you can keep it 0. Now port A, we have connected keyboard, input device, so it needs to be configured as an input port. So 1. Easy to keep in mind. Input I, input 1. It begins with 1 like letter. Output port, it begins with O, similar to 0. That is for easy to keep in mind. Now port A should be connected in the configured in the mode 1. So 0, 1. It is the IO mode control word. So D7 bit is 1. So what is our command? What is our control word for command word? 1011. 1011 means, okay, 1000 means 8 plus 11 means 3. So 8, 9, 10, 11. So this is 11. 11 means 10, 11. A, B. So it should be B. So yeah, it's B. And then LSB 4 bit 0100, it is 4. Okay, B4. So before is the control word that needs to be sent to the control register. But port A keyboard being connected, it is using interrupt driven mode. It is using interrupt driven mode. So internal interrupt enable flip flop for port A, that needs to be enabled. That needs to be enabled. How? By setting the port C off, by setting the port C, say PC4, by setting the PC4 bit to 1. By setting the PC4 bit to 1, we can enable the internal interrupt enable flip flop for port A. Why? I'll be going back also again. Once again, I'll be going back. Why PC4? Okay. We need to set it. So set bit should be in. This is now the BSR mode control word. BSR mode control word for setting PC4 to enable the internal interrupt enable flip flop for port A of 8255A. So fourth bit we need to set. So 1004. We need to set it. So this should be 1. Don't care. For BSR mode control word, you know, D7 bit must be 0. So the corresponding control word is 0000. Okay, 0. Hex digit 0. So LSB 4 bit 01004. Oh, 01. Oh, no. 1001. 1001. Oh, it is 9. So 09. Okay. Now, so this should be the initialization instructions. Now, to check, to send data to the printer. Okay, processor on getting on interrupt from the keyboard through RST 6.5, he should execute an interrupt service routine through which he will be reading the keyboard status. Which way we have read some ADC data, but without 8255A. But here also the concept will be similar. Okay, so here the processor is going to read the keyboard data through an interrupt service routine when the 8255A interrupts the 8085 through RST 6.5, and then processor will be executing corresponding interrupt service routine for reading keyboard data. Forget about that. Interrupt service routine. Forget about that. Now, processor is interfaced with the printer through the status check mode. Now I need to deal with that. Processor can send data to the printer, that means to port B of 8255A, to which actually the printer is connected. The processor will be sending data to the port B that he actually wills to send to printer. Processor will be sending the data to port B when output buffer of port B is not full. That means when the OBF bar, when it is not activated, then processor will be sending the data to be sent to the printer to port B of 8255A. Processor actually sends the data to be printed into the printer. Processor sends the data actually to port B of 8255A. And it will be, data will be stored in 8255A buffer, and whenever printer has time, he will be reading the data from port B. But output, so processor will be sending the data to the port B whenever output buffer full, OBF B for port B, that is deactivated. That means the corresponding buffer is not full. That means when OBF B bar, whenever it is 1. Whenever it is deactivated, when it is 1, then processor will be sending. That means port B buffer is empty. And when the buffer is port B buffer is empty, that means OBF B bar is 1, then processor sends the data to the port B buffer. Now OBF B is low. That means port B of 8255A is loaded, or it is holding the data sent by the processor. Then OBF bar is low. Now processor cannot send the next byte. Processor needs to wait until and unless OBF bar again goes deactivated or again becomes high. That means till the time the printer has not read the byte sent by the 8085 to port B of 8255A. So processor has to wait till the data byte, previously sent data byte, has not been read by the printer. When OBF B bar signal is again deactivated, then processor can send the next byte to the port B with the intention to actually to send it to printer. And now, what is the OBF bar signal? How the processor can get it? The day before I told you through a slide that if processor reads the port C, then if the processor reads the port C, then the status word is pasted into the accumulator. If the processor reads the port C through the in port C address, then the status word will be placed into the accumulator. And D1 bit position indicates the output buffer fullness or emptiness status of port B of 8255A. So we are interested in this D1 bit only. Other bits we are not interested in. So whenever this bit is 1, processor will be sending byte to the port B. Whenever it is 1. So processor needs to keep on checking this bit status. Okay, for the time being, you keep it, because later on I will be again explaining why this PC4 bit we need to set to enable the internal interrupt enable flip-flop of port A. Again, we'll be going back. Otherwise, you can also interpret from whatever slides are covered. But again, I'll be going back. Okay, so you're interested on only this bit position, this one. Okay. Now, let us write a program. Before is the control word that we derived earlier. Before is the control word. To configure port A as input port, port B as output port in handset mode. So, MVI A before, load the control word in accumulator, feed it to the control register. FF is being the address of the control register. C. FF is being the address of the control register. FFH. With this much hardware. Hardware can be anything, address will be differing. Now it depends upon the motherboard designer. He chooses appropriate addresses and make him have an indication in the manual that he has used these addresses for this device. Oh, we have sent the control word. We have configured port A and port B in input output mode respectively, or and in status check mode. In mode 1 we have configured them. Now MBI A09, so as to enable the interrupt enable flip-flop for port A, the BSR mode control word we formed in the previous slide. The BSR mode control word to enable interrupt enable flip-flop for port A, that is PC4 bit. Why I'll be going back later on. So we have loaded the BSR mode control word into accumulator. We have sent it to the control register. But D7 bit for IO mode control word, that is for B4, D7 bit was 1. That is IO mode control word it was. But if you extract 09 in the binary form, D7 bit is 0. It is a BSR mode control word. To set internal enable flip flop, interrupt enable flip flop for port A of 8255A. Now we have enabled the interrupt process by using EI instruction. Because you know on system reset 8085's internal interrupt enable flip flops gets resetted. So, but I need to use interrupt for port A for keyboard. So I need to enable the interrupt process. Then we are going to call a print subroutine, not interrupt service routine. Interrupt service routine there can be for dealing with input data, for dealing with keyboard data, which way we have done for ADC. Maybe by using directly without using 8255. Okay, for the time being, we are forgetting about that interrupt service routine. Only the printer we are going to deal with. This is the printer subroutine. Okay, otherwise this program code can be kept after this EI. No problem. So here also it is better that by using sim instruction you enable on the interrupts. But in this program that has not been done, but that should be done also. You need to unmask all those RST 6.5 and other interrupts if you are going to use them. So MPIA, say what to enable all the interrupts, what was the code we derived earlier? 08H. So MPIA 08H sim. So after using EI, it is better to use MBIA 08H sim. Then this keyboard handling routine. No, not printer handling routine. See, suppose a processor is going to send a number of bytes to the printer. Number of bytes, say 50 bytes or 50 characters for simplicity. So there should be an array of data needs to be sent to the printer. So obviously we need to go for memory pointers. LXIH memory, okay, a memory address. MBIB count value. How many characters ASCII code we need to send to the printer? Okay, the ASCII codes are stored in successive memory locations from these locations onwards. We are assuming it. Now, move M to A. First data byte to be the first byte that is to be printed, get it into accumulator. Move C comma A. Okay, accumulator data, you copy it into the C register. The first byte that is to be printed, that is to be sent to printer. In FE, read port C to get the status of output buffer full. Whenever this output buffer full OBF-B printer is connected to port B, OBF-B bar, whenever this signal is 1, processor can send this byte, the first byte he can send to the port B. Okay, because you know, processor can get this status if the processor reads port C. If processor reads port C, the status word is placed into the accumulator. And D1 is bit position indicates output buffer fullness of port B. D1 bit position we are interested in. If it is 1, processor will be sending C register content to port B of 8255A, to which printer is connected. So let us check. So we got this status word, this status word we got, this status word we got, this bit of major importance to us. A902. So and the status word the processor got with and the status word with 02. 02 means all these bits 00000010. So that means we are ending the status word in such a manner such that only D1 bit position will be get indicated into the result of that AND operation. If D1 bit is 1, result of AND operation will be not 0. If D1 bit or OBF B bar was 0, then result also will be 0, because ending with 02 means the other bits will be obviously 0 except this one, because ending with 0 means 0, but we have to use the term 02. That means all 00000010. So we have logically ended with in such a way such that only this bit get extracted in the final result of this ending operation ANI 02. So if OBF B bar is low after this ending operation, result if OBF bar if it was 0, then after doing AND operation with 02, result also will be 0, because other bits are obviously 0 by ending with 02, but this bit, if this bit was 0, then result also will be 0, but if this bit was 1, result will be not 0. So that way we can check the output buffer full this bit. So you have ended only D1 bit we are interested in. So we have logically ended with the result of the status word by reading the port C of 8255A. The status word got placed with an accumulator. We have logically ended with 02 and jump on 0. Jump on 0. That means OBF B bar is 0. Processor should not send the byte, because it is showing the port B buffer is full. Probably some data is there to be read by the printer. Printer has not read that data byte. So processor cannot send now. When the buffer is empty, then processor sends byte to that empty buffer. So processor waits until and unless OBF B bar becomes high. So whenever ending result results into 0, that means OBF bar is 0. Processor keep on checking the status word again and again until and unless OBF B bar is high. Then processor, when the OBF B bar is high, then processor gets the data from C register to A register. The first byte send it to printer. Not directly to printer, but send it to port B of 8255A, to which printer is connected. Port B acts as a buffer to hold the source data for some time to be read by the receiver and generates the appropriate buffer full signals. Based on that, the source and receiver will be reading or will be sending the next data byte. If the buffer is empty, then source can send the next byte. And if the buffer is full, then receiver can read the byte from the buffer. So has been done. So out to port B register. Port B address is FD. Get the first byte, send it to port B. Which processor wants to actually send to printer? Port B address is FD. Let us have a check. Port B address is FD. Yeah, FD address for port B. So processor has send the data, increment the memory pointer, decrement the counter until and unless the counter becomes 0. Okay, keep on sending the next and next bytes one after another. Okay, they have written a separate subroutine and have called the subroutine from the main program. But instead, this program segment up to JNZ next, you can write in the main program. After EI or after EI, there should be better to use MVI B MVI A 08, then better to use SIM, then better to use this program codes. So here they have written a separate subroutine. You may not use all this program code except this return that can be kept after this EI or after the SIM. Okay, so again say PC4 bit Y to enable the internal interrupt enable flip-flop for port A, while the corresponding bit is PC4. Let us have a check. You have done it in the day before, but say again, let us go through it. Okay. Okay. See, let us. Port A is configured as, this is for input mode. Port A is configured as input port. Yeah, keyboard is connected. See the corresponding status word INTEA. Okay. So this is the, okay, the status. Okay, we are interested in OBF also. OBF B bar. Okay, OBF B bar. Port B is configured as, port B is configured in the output mode. In the output mode. For port B, for input and output pin configuration or status pin positions are same. For port B, INTR B, I say in place of okay. For port B, it will be almost same, but say INTB here in place of this. Okay, some alterations they have made. Okay, some alterations are made. Okay, but say OBF B bar, this bit position, output buffer full. In output mode, its bit position is D1 bit. The status check. The status word will be placed into accumulator if processor reads the port C that is mentioned in some of the slides. So the corresponding bit is D1 bit that we have checked by using AND operation A902. Okay, now to while PC4 for enabling the interrupts of the INTR A. Okay, port A is configured in the input mode. Okay, input mode. Corresponding status word bit positions, 0, 1, 2, 3, 4. PC4. So it is the bit position that you need to set if we want to enable internal interrupt enable flip-flop of port A of 8255A. The bit position is PC4. 0, 1, 2, 3, 4. Got it? This is the bit position. In the input mode of port A. Okay. But in the output mode of port A, the bit position changes. It will be, the bit position will be 0, 1, 2, 3, 4, 5, 6. But port A we have configured as an input port. These are the status word bit positions, status bit positions, before in status signal bit positions that the processor can get if processor reads the port C. Port A we have configured in interrupt driven mode in input mode. Keyboard is connected. Input mode. So this is for input mode. This is the status word bit positions. This bit for enabling the internal interrupt enable flip-flop for port A. What is the bit? 0, 1, 2, 3, 4. PC4 bit, PC4 bit that we have enabled. PC4 bit we have set it to enable the internal enable flip-flop of the port C. Enable the internal interrupt enable flip-flop for port A. Okay. So these are the uh, this is the status word for input mode, considering both A and port B in the input mode. This is for the status word configuration, considering port A and port B both are in output mode. But port A we have configured in the input mode. So for port A signals, this A we need to consider. And for port B we have configured in the output mode. So these signals we need to consider. We have ended with 02 to extract D1 bit position. D1 bit position. And we have enabled the internal interrupt enable flip-flop for port A by setting fourth bit of port C. It is mentioned when the port C is read by the microprocessor, status word is placed into the accumulator. In the input mode and in the output mode, the bit positions are different. Okay. Now, we are going to some another topic. Okay. Now, I'm going to the 8 to say one microcontroller 8051, although it is not actually mentioned in your syllabus, but your syllabus name is microprocessor and microcontroller, but no microcontroller is kept in the syllabus. So at least 2-3 periods next I'll be dedicated for that microcontroller. The syllabus name is microprocessor and microcontroller, but in the syllabus it is not there, but still it will be considered done. 8086 I'll be covering a little bit of it after the microcontroller. Okay, whether you need any 5 minutes break or not. Whether you need any 5 minutes break or not. I think you don't need.
Yes, sir. Yes, sir. You give a 5 minute break.
Okay, it will be then just 5 minutes.
Yes, yes.
Just 5 minutes. Hello students, whether you can start again.
Yes, sir.
Okay, so I'll be discussing a little bit on 8051 microcontroller, Intel developed 40 pin. Okay, so a microprocessor needs to be interfaced with the RAM, ROM, input output ports like 8255A, which provides that interfacing circuitry like address decoding, latch, tri-state buffer. Inside is there 8255A, and he provides that. So microprocessor needs to be interfaced with RAM, ROM, maybe programmable peripheral interfacing devices, some timer circuitry that we can discuss little bit, and UART, serial input output controller. We will discuss this chip later on to build up a microcomputer system. But microcontroller is a single chip microcomputer system in which heart is processor, and its processor is connected within the chip. The processor is being connected with an internal RAM, ROM, input, say programmable, say peripheral interfacing devices, some timer, and some serial communication control devices inside it, inside the microcontroller. The processor internally connected with this RAM, ROM, peripheral interfacing devices, some timer, and serial data communication controller, universal synchronous asynchronous transmitter receiver, UART, universal synchronous asynchronous transmitter receiver. It is processor is internally connected within the microcomputer chip or the microcontroller chip inside. So microcontroller is a single chip microcomputer system where processor is being the main part. Otherwise, to build up a microcomputer system, we need to externally interface the processor with the external data and address bus and control buses. We need to connect the this other memory and input output interfacing circuitry and some other timer or serial input output controller. We need to connect them externally by using external data address and control buses. But within microcontroller, they are connected internally within a single chip. These differences I am not highlighting. We will be going through the difference in detail. But that is the main difference. Single chip microcomputer system is the microcontroller, which is of which microprocessor is being a part. Some program memory, some data memory, some peripheral interfacing circuitries, and some serial controller, serial data transmission receiver controller, some timer control is inside the microcontroller. The processor is connected with those devices internally by using internal buses. Now, pin description of 8051 microcontroller. Okay, okay, it is having with the 4 ports. You see, port 0, 8-bit port, port P0.0, P0.7, an 8-bit port P0, another 8-bit port, port 1, P102, P17, another port, another 8-bit port, port 2, P2. Each individual bits are P20, P2.02, P2.7, and another 8-bit port, another 8-bit port, P3 port. It is also of 8-bit. Each individual bits are P30, P3.02, P3.7. Similar to 8085, a crystal oscillator needs to be connected, or a frequency determining circuit needs to be connected between these two terminals, which determines the operational frequency of 8051. It can operate at 12 megahertz. Very common, that is 12 megahertz it can operate at. Even some more frequency, higher frequency, still it will be, but there will be a maximum limit. Okay. But see here, this constitute the address bus. Yeah. A7, where it is. Okay. AD0 to AD7, then A15, A8 to A15. Okay. A 16-bit external address bus, similar to 8085. So 16-bit external address bus. The same pins, port 2 pins, can be used as the external address bus. Some port 0 pins can also be used as low order address bus, AD0 to AD7. Same low order address, that is A0 to A7, is multiplexed with D0 to D7. Same thing. Again, but not only that, but here there is 3 different purposes of the pin numbers. You may think about P0, P0.0 to P0.7. These bits can be used as an input or output port, or can be used as the low order address bus, A0 to A7, or can be used as the data bus, D0, D1, D2 up to D7. So 3 different purposes. Okay. Only the port 1 pins are not used for any other purpose. Only single purpose. Okay, in the previous slide I have mentioned over here that we can directly connect the digital input output devices to the input output ports of 8051 microcontroller. We can directly connect the digital input output devices to the input output ports of 8051 microcontroller without need of any additional 8255A programmable peripheral interface, or without using 8255A. Also, it doesn't need any address decoder, tri-state buffer, or latch that are generally used for directly interfacing IO devices with 8085 with the processor without using PPI. But if we use the 8255A PPI, then it provides the tri-state buffer, latching, address decoding facility inside is there within 8255A. But if we are using 8051 microcontroller, we don't need even 8255A or any tri-state buffer, address decoder, buffer, latch. 4 8-bit devices can be directly connected to the 4 ports of 8051. Their addresses are fixed. They can be configured as an input port or output port. No need of 8255A address decoder, tri-state buffer, latch. Everything is inside microcontroller. So it is having with the 4 input output ports. P0, port 0, port 1, port 2, port 2, port 3. Each are 8-bit ports. Each are 8-bit ports. And to which we can directly connect digital input output devices. Necessary hardware, programmable peripheral interfacing circuit inside 8051. Okay, but see here, the port 0 pins can be used for 3 different purposes. The same pins here we can connect an input device or output device directly. 8 data pins of the ADC, say 8 set of switches we can directly connect over these pins. Or these pins can also be used as the external address buses to carry the low order address of the 16-bit address bus. It also acts as the low order address bus A0 to A7. Sometimes the same lines are also will be used as data bus, external data bus, through which we can additionally connect additional memory, additional input output devices, other. So another larger, very large memory. Apart from inside RAM and ROM inside the 8085, we can connect some external 64K program memory and 64K data memory. And 64K data memory externally we can connect with this 808551. Apart from the internal 4K program memory and 128 byte internal RAM of 8051. Apart from that, we can additionally externally connect with this 8051 64K data memory plus 64K program memory by using this external address bus and data buses. Sometimes we do not require the external memory. The 80 to 87, sometimes we do not require. If you do not require that much external memory, within the 8051, there is an internal program memory of 4 kilobyte. Generally, our programs we can burn within that area. Generally, we use to burn our programs in that area. Quite enough, 4 kilobyte. And apart from that, it can also support additional 64K data memory plus 64K program memory. They is to be connected through this external data and address buses. So when these pins will be acting as an input port or output port or acting as a data bus or address bus, that will be controlled by these other some control signals. An 8-bit register for multiplication and division operations. So 8051 supports a separate instruction for performing multiplication and division, which 8085 does not provide. But 8051 microcontroller provides the multiplication and division instructions, which requires 2 operands as the inputs. So there should be A and B. Result of multiplication, that can be of 16-bit maximally if we multiply to 8-bit numbers, to 8-bit operands if we multiply, which were stored in A and B register. The result also will be maximally of 16-bit. So result will be stored in AB register together. Result of multiplication of A into B, it will be stored in AB register together. Similarly, for division, two operands you require, which needs to be priorly loaded in A and B register, and result of division, it is consisting of quotient and remainder. So they will be stored in A and B register. Okay. So 8051 supports multiplication and division instructions. Now, program status word, similar to the the flag register. You may think about the like that of the 8085, 8-bit program status word, 8-bit program status word, similar to that of the flag register of 8085. Here it is also 8-bit. Here with the program by PSW, it doesn't mean accumulator plus flag register. No. Here in 8051 by PSW, we mean that PSW or the flag register or program status word. In comparison with 8085, in 8085 by the PSW word, we mean accumulator and flag register together in 8085. But here by PSW we mean only that 8-bit flag register. Stack pointer, memory pointer. So that needs to be off. That needs to be it is of 8-bit. It is of 8-bit. It is going to point to a memory location. Okay. Let me see what happens. Program counter. It is also a memory pointer. It is also pointing to a memory location. 16-bit program counter. Yeah. Very good. Obviously, it should be. Okay. So by on system result, it is registered to 0000H. But stack pointer, it is pointing to a memory location. Then how it is of 8-bit? Yeah. Yeah. See. Within the 8051, there is a program memory of size 4K. That means 4096 bytes. 4K. Requiring how many address lines? 4K. 2 to the power 2 into 2 to the power 10. So 2 to the 12 address lines. So the memory address cannot be denoted by 8-bit. It should be denoted by 12-bit. Okay. In total, by 16-bit, it can be obviously denoted, because internal program memory can be accessed by the 16-bit address. Okay, that's why program counter is 16-bit. 12-bit of it will be used, because internal program memory size is 4K, which requires 12 address lines. So if the address, the memory pointer register is 16-bit, then it can accommodate 12 bits, obvious. No problem. But programs are burned in program memory, but we implement stack in the read-write memory. We implement stack in the read-write memory. We implement stack to be implemented by the programmer by initializing stack pointer, but it is being implemented in read-write memory so that data can be stored in it, data can be retrieved from it without using the double from ROM burning mechanism. So stack should be implemented in the 128-byte data RAM, whose size is 128 byte. Can be addressed by how many bits? 126 bytes of locations can be identified by 2 to the power 7 equals to 128. So they can be addressed by 7 address lines. So internal data RAM can be accessed by the 7 address lines. So they can be accommodated within this 8-bit. So stack pointer of 8051, it is 8-bit stack pointer. And that stack needs to be implemented within this data RAM, 128 byte internal data RAM of 8051. In addition to that, some data pointer register, data pointer, like in 8085 we have used some register pair as the data pointer, but here there is a data pointer register, 16-bit data pointer, DPTR, so as to point to a memory location. Okay, register for serial input output for timers to T0. For two timers are there, two clock inputs T0 and T1. For that, for each of this timer, there is a 16-bit register T0L, T0H for timer 2, T1L, T1H. Then additional some control registers for timer operations, that are T mod register, and T control register for operations of the timer. This may be analogous to the command or control words registers of timer. Timers we will be discussing next day. And interrupt handler, interrupt enable register, interrupt priority register, separate special function registers, interrupt enable register, like that of the SIM, like that of the thing, that bit pattern we need to load into accumulator, then we need to use SIM in 8085. But here, within the interrupt enable register, we can set appropriate masking or enabling or disabling bits. Similarly, interrupt priority register. Okay. Now, hello. I think the time is also up. So, you are becoming impatient. So, I am going to leave then. Hello. Hello, Tamojit. Hello, Tamojit.
Yes, sir. Yes, sir. Sir, please
So,
wait 1 minute. Let me take the attendance.
okay. But previously it was 45, but now it has been a little bit reduced to 38.
Yes, yes. I
Okay.
have taken in
Okay.
between also. Not a
Okay.
problem. Yes, sir. Done.
Okay. So, hello. Okay. So, whether it was understandable. So,
Yes,
if
sir.
it. Okay, okay, okay. Then I am just going to leave. Anything else I have to do? No. Then, okay, I am leaving. Thank you for patient hearing.